Somewhere between Hawaii and the Philippines, far beneath the surface of the Pacific Ocean, lies a scar in the Earth's crust so deep that if you placed Mount Everest inside it, the peak would still be more than a mile underwater. The Mariana Trench stretches for 1,500 miles like a crescent-shaped wound in the ocean floor, and at its deepest point, a place called the Challenger Deep, the water presses down with a force of 8 tons on every square inch. That's the weight of 50 jumbo jets, concentrated into a space smaller than your palm. In the 65 years since humans first reached this place, only 3 manned expeditions have ever descended to the bottom. 3. More people have walked on the moon than have seen the deepest point on Earth with their own eyes. We've sent robots to Mars, probes beyond the solar system, and mapped distant galaxies, yet we know less about the Mariana Trench than we do about the surface of Venus. Not because we lack curiosity or technology, but because the ocean itself won't allow it. The trench sits in the western Pacific, about 200 miles east of the Mariana Islands, near the small island of Guam. It's part of a system of oceanic trenches that form where tectonic plates collide, where the denser Pacific plate dives beneath the smaller Mariana plate in a process that's been happening for tens of millions of years. The trench is ancient, possibly 180 million years old, formed when dinosaurs still walked the Earth. And in all that time, it's remained largely untouched, unexplored, unknown. From the surface, the ocean there looks no different than anywhere else. Blue water, gentle swells, perhaps a few clouds drifting overhead. Nothing betrays what lies beneath. But if you could drain all that water away, you'd see a landscape more dramatic than any mountain range on land. Vast ridges, steep valleys, and at the southern end, a narrow depression that drops deeper than anything else on the planet. The Challenger Deep measures 10,928 meters at its lowest point. To put that in perspective, if you started at sea level and descended straight down, you'd pass the depth where sunlight disappears, the depth where submarines operate, the depth where whales dive, and you'd still have miles to go. The journey down takes hours. Not because the distance is so great in terms of miles, it's only about 7 miles after all, but because every meter adds more pressure, more weight, more resistance. By the time you reach 1,000 meters, sunlight has faded to nothing. By 3,000 meters, the pressure is 300 times what you feel standing on the beach. And at the bottom, at nearly 11,000 meters, the water above you weighs more than anything humans have ever tried to withstand. 1,086 bars of pressure, 15,750 pounds per square inch, the equivalent of having 100 elephants standing on your head. At that depth, water behaves differently. It becomes denser, heavier, more like liquid metal than the water you know from swimming pools or bathtubs. Steel compresses, titanium bends, glass shatters instantly. Even air itself, if it were somehow contained at that pressure, would collapse into liquid. The cold doesn't help. Despite being near the equator, the temperature at the bottom of the Challenger Deep hovers between 1 and 4 degrees Celsius, just above freezing. There's no warmth down there, no light, no sound, except the creaking of whatever vessel dares to descend. It's as close to absolute emptiness as you can get while still being on Earth. And yet, life exists there. Strange, translucent creatures that have never seen sunlight. Fish with bodies like jelly and bones, replaced by cartilage. Amphipods the size of your hand, pale and ghostly, scavenging whatever drifts down from above. Bacteria living in the mud, feeding on chemicals leaking from the Earth's crust. They've adapted to conditions that would kill any surface creature in seconds, evolving in darkness and pressure so extreme it seems impossible. But they don't just survive. They thrive, moving slowly through a world we can barely imagine. The trench itself formed through a process as violent as it is slow. The Pacific Plate, one of the largest tectonic plates on Earth, collides with the Mariana Plate at a rate of a few centimeters per year. Not fast by human standards, but over millions of years. That movement carves trenches, builds volcanic islands, and reshapes entire regions of the sea floor. The Pacific Plate, being older and denser, gets forced downward, bending the ocean floor into a deep V-shaped valley. As it descends, it releases water trapped in its minerals, and that water rises into the mantle above, causing flux melting that creates the volcanic Mariana Islands on the surface. The whole system is connected, a massive geological engine that's been running for longer than mammals have existed. For most of human history, we had no idea the trench existed. Ancient sailors crossed the Pacific for thousands of years without knowing what lay beneath them. It wasn't until the mid-19th century, when oceanography began as a science, that we started probing the depths. The first attempt to measure the trench came in 1875 during the Challenger expedition, a British voyage that circumnavigated the globe studying ocean currents, temperatures, and depths. Using a weighted rope, literally just a long line with a weight at the end, the crew recorded a depth of 4,475 fathoms, about 8,000 meters. They called the location Challenger Deep, and that name stuck. But weighted ropes aren't precise. The rope could drift with currents, the weight could snag on rocks, and at such depths, it was hard to tell when the line actually hit bottom. In 1951, the British survey vessel Challenger 2 returned to the area with better technology, echo sounding, which uses sound waves bounced off the seafloor to measure depth. This method revealed the trench was even deeper than previously thought, nearly 11,000 meters. Finally, we had an accurate picture of just how far down the ocean could go. Yet knowing the depth and actually reaching it are two different things. For the ocean doesn't welcome visitors. It presses back against every attempt to enter it, and the deeper you go, the harder it pushes. At the surface, atmospheric pressure is roughly 14.7 pounds per square inch, or 1 bar. That's the pressure your body is designed for, the pressure you've felt every moment of your life without noticing. But in the ocean, pressure increases by 1 atmosphere for every 10 meters you descend. At 100 meters, you're experiencing 10 times surface pressure. At 1,000 meters, 100 times. At 10,000 meters, you're under 1,000 atmospheres, and your body, if exposed, would collapse in an instant. Human beings can dive to remarkable depths with training and the right equipment. Free divers, holding their breath, can reach over 100 meters. Scuba divers with specialized gas. Mixtures can go deeper, though beyond 300 meters, the risk of nitrogen narcosis, oxygen toxicity, and decompression sickness becomes lethal. The deepest anyone has ever dived on compressed air is around 300 meters, achieved by a handful of professional divers who spent years preparing. Beyond that, human exploration ends. The pressure is simply too great for our bodies to withstand, no matter how much training or technology we use. So we build machines, vessels designed to carry us into environments we can't survive on our own. Submarines, bathyscaphs, submersibles, each one a tiny pocket of breathable air surrounded by thick walls of metal or composite materials, sealed against the crushing force outside. But even these machines have limits. A typical military submarine operates at depths of around 300 to 600 meters. Nuclear submarines might go as deep as 600 to 900 meters. Specialized research submersibles can reach 3,000 to 6,000 meters, which covers most of the ocean floor. But the Mariana Trench lies nearly twice as deep as even those vehicles can go. To reach the bottom, you need something extraordinary, something designed not just to survive the pressure, but to function under it. And over the past 65 years, only a handful of such vessels have ever been built. The first was called the Trieste. It was designed by Auguste Piccard, a Swiss scientist who had previously broken altitude records in balloons by applying principles of buoyancy in reverse. If buoyancy could lift a balloon into the stratosphere, Piccard reasoned, it could also control descent into the ocean. He designed a bathyscaphe, from the Greek words for deep and vessel, that consisted of a thick steel pressure sphere suspended beneath a large tank filled with gasoline. Gasoline is less dense than water, providing buoyancy, while iron pellets in hoppers provided weight to sink. Release the pellets, and the vessel would rise. It was elegant in its simplicity, though terrifying in its execution. The Trieste was built in Italy and launched in 1953. It spent several years conducting dives in the Mediterranean, testing its systems, proving it could withstand extreme depths. In 1958, the United States Navy purchased it for $250,000 and transported it to San Diego, California. There, it was fitted with a new pressure sphere, this one made by the Krupp Iron Works in Germany, designed to withstand the pressures of the deepest ocean. The sphere was small, barely 2 meters in diameter, with walls of steel nearly 13 centimeters thick. Inside, there was just enough room for 2 men sitting shoulder to shoulder, surrounded by instruments and emergency systems. It had a single small window made of plexiglass, several inches thick, through which the occupants could peer into the darkness outside. On January 23, 1960, the Trieste was towed to a position above the Challenger Deep, about 200 miles southwest of Guam. The weather was rough, with 25-foot swells, and the conditions didn't look promising. But after checking the systems, the decision was made to proceed. Jacques Piccard, Auguste's son and co-designer of the bathyscaphe, climbed into the sphere along with Don Walsh, a U.S. Navy lieutenant. They sealed the hatch, a 430-pound steel door bolted shut from the outside, and began their descent. The journey down took 4 hours and 47 minutes. The Trieste sank slowly, about 3 feet per second, dropping through layers of water that grew darker and colder with every passing minute. At 100 meters, the sunlight was fading to a deep blue. At 500 meters, only the faintest glow remained. By 1,000 meters, they were in complete darkness, the only light coming from the submersible's own instruments. The temperature inside the sphere dropped steadily. The men wore minimal clothing, just enough to stay warm in the cramped, unheated space. Outside, the water temperature plummeted to just above freezing. As they descended past 9,000 meters, they heard a loud crack. It shook the entire vessel, a sharp, explosive sound that echoed through the sphere. Walsh looked out the rear viewport and saw the problem. One of the outer plexiglass windows in the entry tube had cracked under the pressure. The entry tube was free flooding, meaning it filled with water during the dive, so the crack wouldn't cause an implosion. But it did mean that if they couldn't blow the water out of the tube when they surfaced, they'd be trapped inside the sphere until the Trieste could be towed back to Guam, a journey of 4 days. Still, they decided to continue. They'd come too far to turn back now. At around 35,000 feet, the instruments indicated they were approaching the bottom. Picard and Walsh peered out the tiny viewport, straining to see anything in the blackness. The submersible's floodlights illuminated only a few meters ahead, revealing a pale, featureless expanse of sediment. The bottom appeared as Auguste Piccard would later describe it: light and clear, a waste of firm diatomaceous ooze. Diatomaceous ooze is a type of sediment made from the remains of microscopic organisms called diatoms, their silica shells compressed over millions of years into a fine, almost powdery mud. They touched down gently, the Trieste settling into the soft bottom at a depth of 10,916 meters, 35,814 feet. For the first time in history, human beings had reached the deepest point on Earth. They stayed for 20 minutes, not because they wanted to leave, but because the sediment they'd stirred up during landing filled the water with a thick cloud, obscuring visibility. They couldn't see more than a few feet in any direction. The cameras they'd brought, a 16mm movie camera and a Hasselblad still camera, were useless. No photographs could be taken, but they did observe something remarkable. Through the viewport, Piccard saw what he believed to be a flatfish, about a foot long, lying on the bottom. It was pale, almost translucent, and it moved slightly as if disturbed by their arrival. The sighting was controversial. Many marine biologists later questioned whether it could have been a fish at all, since the theoretical maximum depth for vertebrates is around 8,000 to 8,500 meters. Beyond that, the pressure is believed to make it impossible for fish to maintain the necessary osmotic balance. Some suggested it might have been a sea cucumber or another invertebrate, but Piccard was certain of what he saw, and for him, it answered a question that had puzzled scientists for decades. Could life exist in the greatest depths of the ocean? According to his observation, it could. After 20 minutes on the bottom, they released the ballast, steel pellets that dropped away into the sediment, and began their ascent. The journey back to the surface took 3 hours and 15 minutes, slightly faster than the descent. When they finally emerged into daylight, they were greeted by the crew aboard the destroyer escort USS Lewis, which had been monitoring their progress from above. The dive was complete. They'd proven it was possible to reach the deepest place on Earth and return safely, but they'd also revealed just how limited such a visit could be. 20 minutes, a few cloudy glimpses of the bottom, no samples, no detailed observations, no scientific data beyond the fact that they'd survived. And then, for more than 50 years, no one went back. The reason wasn't lack of interest. Scientists desperately wanted to study the trench, to understand what lived there, how it had formed, what secrets it held. But the cost and complexity of building a vessel capable of reaching those depths were staggering. The Trieste had been expensive to operate, and it had proven difficult to control. It couldn't maneuver well, couldn't take photographs or collect samples, and it required a massive support operation just to function. After the Challenger deep dive, the Trieste was repurposed for other missions, including searching for the wreckage of the USS Thresher, a nuclear submarine that sank in 1963. But no one attempted another crewed dive to the bottom of the Mariana Trench. Technology improved over the following decades. Remotely operated vehicles, or ROVs, became more sophisticated, capable of diving deeper and staying down longer than any human-occupied vessel. In 1995, the Japanese unmanned submarine Kaiko descended to the Challenger Deep and collected samples of sediment and small organisms. It was a scientific success, proving that robots could reach the trench and perform useful work. Then, In 2009, the U.S. hybrid remotely operated vehicle Nereus made the journey, spending 10 hours on the bottom, recording video and gathering biological samples. But in 2014, Nereus imploded while exploring the Mariana Trench, another deep-sea location. The vessel simply crumpled under the pressure, a reminder that even unmanned vehicles are fragile in such extreme environments. Still, no human had returned to the Challenger Deep, until James Cameron decided he wanted to go. Cameron, best known as the director of films like Titanic, Avatar, and The Abyss, had always been fascinated by the ocean. He'd made numerous dives to the wreck of the Titanic during the filming of his Academy Award-winning movie, and he'd spent years developing underwater camera technology. The idea of diving to the deepest point on Earth appealed to him not just as a filmmaker, but as an explorer. In 2009, he began working with a team of engineers in Australia to design a submersible capable of making the journey. The result was the Deep-Sea Challenger, a vessel unlike anything that had come before. Instead of the spherical design used by most submersibles, the Deep-Sea Challenger was tall and narrow, shaped like a vertical torpedo. It stood 24 feet high, but was only a few feet wide, designed to descend quickly by minimizing drag. The pilot sphere, where Cameron would sit, was located near the bottom of the craft, a cramped space just 43 inches in diameter. Cameron would have to sit with his knees bent for the entire dive, unable to move much, surrounded by controls and monitors. The submersible was made primarily of syntactic foam, a specialized material consisting of hollow glass spheres embedded in resin. This foam is strong enough to resist compression at extreme depths, while remaining buoyant enough to help the craft ascend. Traditional submersibles used gasoline-filled floats like the Trieste, but syntactic foam was lighter, stronger, and more reliable. The pressure sphere itself was forged from a single piece of steel, with walls thick enough to withstand the crushing force of the deep. On March 26, 2012, after months of testing and preparation, Cameron climbed into the Deep-Sea Challenger and began his descent. The craft was launched from the research vessel Mermaid Sapphire, lowered into the water by a crane, and released. It sank quickly, descending at a rate of about 500 feet per minute, far faster than the Trieste. Cameron monitored the instruments as the light outside faded from blue to black. He passed through the abyssal zone, where bioluminescent creatures glowed faintly in the darkness. He watched the depth gauge tick upward, 5,000 meters, 8,000, 10,000. The descent took 2 hours and 36 minutes. As he approached the bottom, Cameron slowed the craft and switched on the floodlights. The seafloor came into view, pale and barren, covered in fine sediment. He touched down gently at a depth of 10,908 meters, 35,787 feet. It was the deepest solo dive in history, and Cameron was only the third person ever to see the Challenger Deep with his own eyes. He spent nearly 3 hours on the bottom, far longer than Piccard and Walsh had managed. He maneuvered the submersible across the sea floor, filming with multiple high-definition cameras and collecting samples using a mechanical arm. But almost immediately, things started going wrong. The extreme pressure took a toll on the equipment. Batteries drained faster than expected. The sonar system died completely. 2 of the 3 starboard thrusters failed, making the craft sluggish and hard to control. Cameron's compass began glitching, making navigation difficult. He described the experience later as being like flying a plane with half the instruments out. Still, he managed to collect scientific data. The cameras captured footage of the barren landscape, which Cameron described as looking very lunar. There were no large creatures visible, no fish, no obvious signs of life. Just pale sediment stretching in every direction, illuminated only by the submersible's lights. The mechanical arm scooped up samples of mud and small rocks, which would later be analyzed and found to contain 68 new species, mostly bacteria, but also some small invertebrates. It was a significant scientific achievement, proof that even at the deepest point on Earth, life found a way. After nearly 3 hours, Cameron decided it was time to ascend. He released the ballast weights, steel plates bolted to the bottom of the craft, and the deep-sea Challenger shot upward. The ascent took about 70 minutes, much faster than the descent. When Cameron surfaced, blinking in the sudden brightness of daylight, he was exhausted but elated. He'd done it. He'd reached the bottom of the world and returned safely. But he also understood, more than ever, just how difficult true exploration of the trench would be. 3 hours on the bottom, exploring only a tiny patch of seafloor, with equipment failures limiting what he could accomplish. The trench had allowed him to visit, but it had made him work for every second. And then, in 2019, another explorer decided to go even further. Victor Vescovo, a retired naval officer, private equity investor, and extreme adventurer, had already climbed the 7 summits and reached both the North and South Poles. But he wanted to do something no one else had ever done: reach the deepest point in all 5 of the world's oceans. He called it the 5 Deeps Expedition, and he commissioned a submersible specifically designed for the task. The vessel, called the DSV Limiting Factor, was built by Triton Submarines in Florida and certified for full ocean depth by the classification society DNV-GL. It was the first commercially certified submersible capable of reaching any point on Earth's seafloor. The Limiting Factor was a 2-person submersible with a titanium pressure sphere 3.5 inches thick. Unlike the deep-sea Challenger, which was designed for a single dive, the Limiting Factor was built for repeated use. It could descend and ascend quickly, spend extended periods on the bottom, and handle multiple dives in rapid succession. It was, in many ways, the culmination of everything engineers had learned from 60 years of deep-sea exploration. On April 28, 2019, Vescovo piloted the Limiting Factor to the bottom of the Challenger Deep. He reached a depth of 10,928 meters, 35,853 feet, 16 meters deeper than any previous dive. It was a new world record. He spent 4 hours on the bottom, exploring the seafloor and collecting samples. Then, on May 1st, he did it again, completing a second solo dive to the same depth. He spent another 3.5 hours on the bottom, this time exploring the southern rocky slope of the deep. Between April 28th and May 5th, the Limiting Factor completed 4 dives to the Challenger Deep and 1 additional dive to the Sirena Deep, another part of the Mariana Trench about 128 miles to the northeast. It was an unprecedented achievement. For the first time, a submersible had proven it could reach the deepest point on Earth reliably and repeatedly, like a bus making regular runs. But even with all this success, Vescovo's dives revealed the same fundamental problem that had plagued every previous attempt. You can reach the trench, but you can't stay. Each dive took 3.5 hours to descend, 3.5 to ascend, and a few hours on the bottom. The Limiting Factor could theoretically support 2 people for 4 days, but no one has ever attempted such a prolonged stay. The psychological toll, the physical discomfort, the risk of equipment failure, all of it makes extended missions impractical. And even if you could stay for days, you'd still only be able to explore a tiny fraction of the trench. The Challenger. Deep alone covers an area of several square kilometers. The entire Mariana Trench stretches for 1,500 miles. To map it comprehensively would require thousands of dives over decades, and even then, you'd only have a snapshot of a landscape that's constantly shifting, constantly changing. Which brings us to the heart of the question: why can't we really explore the Mariana Trench? The answer isn't simple. It's not just one obstacle, but a combination of factors: physical, technological, economic, and even philosophical, that conspire to keep the trench beyond our reach. Start with the engineering. Every component of a deep-sea submersible must be designed to withstand pressure that would crush almost anything else. At the bottom of the Challenger Deep, the pressure is over 16,000 pounds per square inch. To put that in perspective, a typical car tire is inflated to about 35 psi. The Challenger. Deep has pressure more than 400 times greater than that, pressing in from every direction. Materials behave differently under such conditions. Steel compresses. Aluminum deforms. Even titanium, one of the strongest metals available, can only resist so much before it begins to yield. The solution is to design the pressure hull as a perfect sphere or near sphere, because a sphere distributes pressure evenly across its surface. Any flat area, any corner, any imperfection becomes a weak point where the pressure can concentrate and cause failure. That's why the crew compartments of deep-sea submersibles are always spherical. It's not just for aesthetics, it's a matter of survival. But a sphere is also an inefficient shape for a vessel. It's hard to pack equipment into, difficult to maneuver, and limits the internal volume. The Trieste sphere was only 2 meters across. The deep-sea Challenger's was 43 inches. The limiting factors is slightly larger, but still cramped. You can't fit much scientific equipment into such a small space, and you certainly can't bring more than 1 or 2 people. Then, there's the problem of buoyancy. A submersible needs to sink to reach the bottom, but it also needs to rise again when the mission is complete. The Trieste used gasoline for buoyancy and iron pellets for ballast. When the pellets were released, the gasoline's natural buoyancy lifted the vessel back to the surface. Modern submersibles use syntactic foam instead of gasoline, but the principle is the same: balance weight and buoyancy, so the craft can descend and ascend safely. This limits how much equipment you can carry. Every additional sensor, every camera, every sample container adds weight, which means you need more buoyancy to compensate, which makes the submersible larger, which increases drag, which slows descent and ascent. It's a delicate balance, and there's only so much you can optimize before you hit hard physical limits. Communication is another massive challenge. Radio waves don't travel through water, so you can't use traditional radio to communicate with the surface. Instead, submersibles rely on acoustic modems, which convert voice or data into sound waves that travel through the water. But sound moves slowly compared to radio, and it's easily distorted by temperature layers, salinity gradients, and pressure differences. A message sent from the Challenger Deep takes about 7 seconds to reach the surface, and another 7 seconds for a reply to come back. That's a 14-second delay for every exchange, and that's if the communication works at all. Often, the signal is garbled or lost entirely, forcing the pilot to switch to text messaging, which is even slower. During the Trieste dive, Picard and Walsh could communicate with the surface ship, but the delay was so long that real-time conversation was impossible. Cameron, in the deep-sea Challenger, lost all communication for stretches of the dive. Vescovo had better systems, but even he experienced dropouts and delays. This communication blackout means that a submersible descending into the trench is essentially on its own. If something goes wrong, there's no way to get help. If the pilot becomes disoriented, there's no one to guide them. If equipment fails, there's no technician who can talk them through repairs. The crew on the surface can monitor basic telemetry, depth, temperature, pressure, but they can't see what the pilot sees or make decisions in real time. It's like flying a plane through a storm with the radio out and no instruments. You're alone, in the dark, under crushing pressure, with no margin for error. And if something goes catastrophically wrong, if the pressure hull cracks, if the ballast release fails, if the thrusters stop working, there's no rescue. You can't send divers down to help. You can't deploy another submersible in time. You're too deep, too isolated, too far from any support. The ocean doesn't allow second chances. This reality weighs on every person who descends into the trench. They know that once they pass a certain depth, they're committed. There's no turning back, no calling for help, no escape, except through the same route they came. It's not fear exactly. Most deep-sea explorers are too experienced for that. But it's a constant awareness of vulnerability that never quite fades. Then there's the cost. Building a submersible capable of reaching full ocean depth costs tens of millions of dollars. The Deep-Sea Challenger was estimated at around $50 million, including development and testing. The DSV limiting factor cost approximately $37 million. And that's just the submersible itself. You also need a support ship, which can cost millions more to build or charter. You need a highly trained crew, pilots, engineers, technicians, scientists, all of whom require months or years of specialized training. You need spare parts, backup systems, and contingency plans for every possible failure mode. A single dive to the Challenger Deep costs thousands of dollars per minute of bottom time, and most funding agencies balk at such expenses when the scientific return is uncertain. Because that's another problem. What do you actually learn from visiting the trench? Yes, you can collect samples, take photographs, make measurements. But the trench is so vast, and each dive explores such a tiny area that the data you gather is necessarily limited. It's like trying to understand the Sahara Desert by studying a single square meter of sand. You might learn something interesting about that particular spot, but you can't extrapolate much to the rest of the environment. To truly explore the Mariana Trench, you'd need hundreds or thousands of dives, covering different areas, different depths, different seasons. You'd need to map the entire trench at high resolution, catalog every species, measure every current and temperature gradient. And even then, you'd only have a snapshot of a dynamic system that's constantly changing. The trench isn't static. Sediments shift with deep ocean currents. Organisms migrate. Hydrothermal vents open and close. Earthquakes reshape the sea floor. What you observe on one dive might not be there on the next. This makes long-term scientific studies incredibly difficult. Unlike terrestrial field research, where you can set up a camp and observe a location over months or years, deep-sea research happens in brief, disconnected bursts. You visit, you observe, you leave. Then you come back weeks or months later, and everything has changed. And there's the biological impact to consider. Every time a submersible descends into the trench, it disturbs the environment. The lights blind creatures adapted to total darkness. The thrusters stir up sediment, obscuring visibility and disrupting the sea floor. The mechanical arms used to collect samples crush delicate organisms. even the sound of the submersible's motors, amplified by the water, might alter animal behavior. Marine biologists call this the observer effect. The act of observation changes what's being observed. In the deep ocean, where life is so sparse and fragile, this effect is magnified. Some species might flee from the submersible, while others might be attracted to the lights or heat. You can never be sure whether what you're seeing is natural behavior or a response to your presence. Then there's the problem of bringing samples back. Most deep-sea creatures are adapted to extreme pressure. Their cells, their proteins, their entire biochemistry is built around the assumption that they'll always be under 1,000 atmospheres. When you collect a specimen and bring it to the surface, the rapid decompression kills it almost instantly. The pressure drop causes gases dissolved in their tissues to expand, essentially giving them decompression sickness. Their bodies swell, rupture, and die. Even if you use special pressurized containers to keep them alive during ascent, you can only maintain that pressure for so long before the equipment fails or the specimen dies from stress. This means that most deep-sea organisms have never been studied alive. We only know them from dead specimens, and we can only guess at how they behaved in their natural environment. There's also a psychological dimension to deep-sea exploration that's rarely discussed. The people who pilot these submersibles spend hours in cramped, dark, cold spaces under conditions that would drive most people to panic. The descent alone takes several hours, and during that time, there's nothing to see outside the viewport except blackness. No horizon, no landmarks, no sense of motion except the numbers on the depth gauge slowly ticking upward. Some pilots describe it as meditative, a chance to clear their mind and focus entirely on the mission. Others find it deeply unsettling, a confrontation with their own insignificance in the face of the ocean's vastness. Once you reach the bottom, the isolation intensifies. You're 7 miles below the surface, farther from other human beings than astronauts on the International Space Station. If something goes wrong, there's no one who can help. You're surrounded by darkness so complete that even with floodlights, you can only see a few meters ahead. The pressure outside is enough to crush you instantly if the hull fails. And yet, you have to stay calm, focused, operating complex equipment in an environment that's fundamentally hostile to your existence. It's not surprising that so few people have attempted it. The psychological requirements are almost as demanding as the physical ones. And then there's time. Even if you had unlimited funding and the perfect submersible, you're still constrained by the simple fact that every dive takes an entire day. 3 to 4 hours to descend, a few hours on the bottom, 3 to 4 hours to ascend, and then at least a day to recharge batteries, check systems, and prepare for the next dive. If you wanted to explore just the Challenger Deep comprehensively, visiting every square kilometer at least once, you'd need hundreds of dives. Spread that out over years, accounting for weather delays, equipment maintenance, and crew schedules, and you're looking at a decades-long project. And that's just for one small part of one trench. The Mariana Trench is 1,500 miles long and 69 kilometers wide on average. There are other trenches in other oceans, some almost as deep. The global Hadal Zone, the region of the ocean deeper than 6,000 meters, covers an area roughly the size of Australia. To map and study all of it would take centuries using current technology. And by then, the environment will have changed, requiring you to start over. It's a Sisyphean task, forever incomplete. But perhaps the deepest reason we can't truly explore the Mariana Trench isn't technological or economic. It's philosophical. The ocean, in some fundamental way, resists human presence. We're land creatures, evolved for air and light and moderate pressures. The deep sea is antithetical to everything our bodies and minds are designed for. We can visit it, briefly, in carefully engineered vessels that protect us from instant death. But we can't live there, can't build permanent structures there, can't stay long enough to truly understand it. The ocean tolerates our visits, but it never welcomes us, and maybe that's okay. Maybe some places should remain beyond our full reach, not because we lack the technology, but because they remind us that the world is larger than our ability to control it. The Mariana Trench doesn't exist for us. It's not waiting to be explored, mapped, and catalogued. It simply is, doing what it's done for 180 million years, completely indifferent to whether we ever understand it. There's value in that mystery. In an age where almost everything feels knowable, where satellites map every inch of land and algorithms predict our behavior, the trench stands as a reminder that some questions don't have easy answers. Some places don't yield their secrets just because we want them. The ocean keeps its own counsel, operating on timescales and scales that dwarf our brief human lifespans. The 3 expeditions that reached the Challenger Deep, Picard and Walsh in 1960, Cameron in 2012, Vescovo in 2019, proved that visiting is possible. But they also revealed how limited those visits are. 20 minutes here, 3 hours there, a few hours more. Brief glimpses into a world that stretches for miles in every direction. A world we can see, but never truly inhabit. Each dive gathered valuable data, discovered new species, expanded our understanding. But each dive also underscored how much remains unknown, how much will likely always remain unknown. Because the trench doesn't care about our curiosity. It doesn't reward our ingenuity or admire our courage. It simply exists, pressing down with 8 tons per square inch, cold and dark and silent, waiting. Not for us, it's not waiting at all. It's just there, as it has been for longer than our species has existed, as it will be long after we're gone. And in the end, maybe that's the answer. We can't really explore the Mariana Trench because the ocean itself won't allow it. Not out of malice, but out of simple physics. The pressure is too great, the darkness too complete, the environment too hostile. We can visit, we can study, we can learn. But we can't stay. We can't map every inch, understand every organism, answer every question. Some mysteries persist, not because we're not clever enough, but because they're too vast, too deep, too fundamentally other. The trench will keep its secrets. And perhaps, in a world where so much has been discovered and explained, that's not such a bad thing. Perhaps we need a frontier that remains beyond reach, a reminder that for all our technology and ambition, we're still small creatures in a very large universe. The ocean taught us that. The Mariana Trench continues to teach it every time someone descends into its depths and realizes just how brief, how fragile, how temporary their presence there truly is. Somewhere beneath the surface of the Pacific, miles below where sunlight fades to nothing, the trench continues its slow work. Sediments drift downward, settling layer upon layer. Creatures too strange to imagine move through the darkness, feeding on what little drifts down from above. Tectonic plates grind together, millimeter by millimeter, reshaping the sea floor. And above it all, the weight of an entire ocean presses down, unchanging, eternal, indifferent. We've seen it. We've touched the bottom. We've proven we can get there and return. But we haven't really explored it, not truly, not in any way that would satisfy our desire to know, to understand, to master. The Mariana Trench remains what it's always been, the deepest shadow on Earth, a place where human ambition meets its limit, where curiosity confronts the simple, undeniable fact that some things will always be beyond us. And as you drift off to sleep tonight, maybe there's comfort in that. Knowing that beneath the familiar world of cities and roads and artificial light, there exists a place unchanged by our presence. A place where the darkness is complete, where the pressure equals the weight of the world, where life persists in forms we can barely comprehend. A place we can visit, but never claim. A place that reminds us, in the quietest possible way, that the earth still holds mysteries we'll never fully solve. The Mariana Trench doesn't need us, but perhaps we need it, not to conquer, not to map, not to understand completely, but to know it's there. To know that somewhere, 7 miles down, in cold and darkness and crushing pressure, the ocean keeps its secrets, and will keep them long after we've stopped asking. Good night, fellas. Sleep deep and dream big. See you next night.